Hello and welcome to the video for the second half of the first homework of Chapter 2. We're going to do page 54, numbers 9 to 13, starting at problem 9. Neither of the following graphs has a Hamiltonian circuit. Is it possible to add a single edge to these graphs to obtain a graph that has a Hamiltonian circuit? So, part A, we're looking at this graph. The easiest way I think of to try to make a complete Hamiltonian path is going to be going across here, down, across there, and then down here. So if we're going to add a single edge to make a Hamiltonian circuit, I would just go from there to there. And here that's from C to A, so I could say we would add edge CA, or AC, it's the exact same edge. Part B, we're looking at this graph. Lots of ways we could do this. Like if I think of going across, down, just kind of going around, I could add the edge in there. I could go around, well I guess there's no point in talking about multiple. I can just go around here also and add that edge. I guess the point I'm making is whatever path you make, just add an edge from wherever you end to wherever you started, as long as you cover every vertex. So in our case that was from x5 to x1. So I could add edge x5, x1, and that would do it. Question 9, part B, is, if I can do this, well, alright, it's over here. 9, part B. Find an example of a graph that has no Hamiltonian circuit and will still have no Hamiltonian circuit no matter what single edge is added to it. So the key is that we can only add one edge. So I just think of, if I do this, it's totally disconnected. No matter what edge I add, I could connect A and B, or I could connect B and C, or I could connect A and C. There will be no Hamiltonian circuit because it still will be disconnected. I think that's the simplest solution, but there are an infinite number of solutions. You may have come up with lots of different ones. Question 10. Explain why the graph below has no Hamiltonian circuit. Well, is that the graph we're looking at? Oh no, there's a 9C, my bad. 9C shows possible to add four additional edges to the graph in part B so that the resulting new graph will still have no Hamiltonian circuit. So this question I think is the hardest question in the entire homework, so I'll spend a little bit of time discussing it. Here is the way I think about it. I have to add four edges to this in such a way that there is no Hamiltonian circuit. Well, I guess one way I could do it is just duplicating existing edges. That might be the easiest. Here's what I had thought of. We talked in class about how if I think of these as red dots, then I have 5 red dots, and these as blue dots, then I have 4 blue dots. So I could do, there's my red dots, there's my blue dots. To keep things straight, I'll call this x1, x3, x9, x7, and x5, and I'll call these x2, 2, 8, 4, and 6. So x1 connects to x2 and x8, x3 connects to x2 and x4, x7 connects to x8 and x6, and x5 connects to 4 and 6. x9 is the one vertex that connects to every dot of the other color, so every blue dot, I believe I'd said. Now I need to add 4 edges in such a way that this still has no Hamiltonian circuit. Well, I can connect anything as long as I don't connect a red dot to a red dot or a blue dot to a blue dot. So I could connect x1 is not connected yet to x4 or x6. x3 is not connected to x8 or x6. So that would be 4 edges, and the 4 edges I added, I connected 1, 2, where's x4? x4 and x6, and I connected x3 to x8 and x6. Those would be 4 edges that I could add, and still here there will be no Hamiltonian circuit. It's obvious when you look here, much harder to see over here. But this is kind of what's cool about the way the math works, is if you understand how these graphs are related, it makes a concept that is very difficult over here, very simple over here, and then the hard part is just translating back and forth between the two of them. Now on to problem 10. So we want to explain why that graph there has no Hamiltonian circuit. Well, that graph there looks like this graph. So this has valence 2, and this has valence 2, and this has valence 2. So there are lots of different ways I could describe this, but I could say this is D, C, and B. So since D, C, and B are all 2-valent, and every edge connects to one of them, I can specify at least, because there are plenty of edges that, no, there aren't actually. There are no edges that connect to both of them. Every edge connects to exactly one of them. So every edge must be included. So a Hamilton circuit I won't start 11 there, will also be an Euler circuit, and here's A. Since A is 3-valent, this is not possible. This is one argument that I see as easy, saying that there's no way this could have a Hamilton circuit. The other argument you could make that would be easy is you could say this section here must be part of it, and that section is a cycle. You can't have a smaller cycle as part of a Hamilton circuit, because then you must have either visited A or E multiple times. So there's another argument you could have made that is equivalent. Problem 11 says, use the graph in exercise 10 to help you construct a connected graph where every vertex has valence 3 and it doesn't have a Hamilton circuit. So up here I have valence 3 and valence 3, and then valences are 2, 2, and 2. I don't see an easy way to fix the valence of vertex C, so instead when I use this, I'm going to simply delete C completely. So I'm going to use this type of thing. Now I have valence 3, valence 3, valence 2, valence 2. So these are the only two places that I have to fix that valence, so I'm going to connect that to something else. Now this piece is 1-valent, so there's 2 and 3, and the way I'll fix those is I'll just do another one of these things. Now I have the exact same problem, but this is now has valence 3, this also now has been fixed, and if I do the same thing, now I have something that is symmetrical. I just need to do the same stuff on the other side. Now that's 3, and it just works. The hardest part to describe is why I just want to delete vertex C, and the easiest thing I can say about that is it's just the easiest way I think to fix it when I look at this and say, like, I need that to be valence 3 or to go away, and it's easier to just delete that one. Yeah. Question 12. Explain that why the tour A, B, C, F, E, C, B, D, A is not a Hamiltonian circuit. Well, we used BC twice. That is why it's not a Hamilton circuit. Does this graph have a Hamiltonian circuit? Well, it was A, B, C, F, E, C, B, D, A. Used, I'll just say vertex C multiple times. Therefore, it's not a Hamilton circuit. Does this graph have a Hamilton circuit? Well, I have to include that edge and that edge because this is 2-valent, and I have to include that edge and that edge because this is 2-valent. That creates a small cycle as part of it, so no, it doesn't have a Hamilton circuit. It doesn't ask why. I can simply move on, and this is the last question, 13. First of all, do the following graphs have Hamiltonian circuits, and if not, why not? So, A, I have to include those edges because it's 2-valent, those edges because it's 2-valent, and those edges because that's 2-valent. I can't have 3 edges meet there, so no. Why not? Because, and this video is getting long, so I'll just describe it. These edges must be included because of the 2-valence argument. 3 edges can't meet there, otherwise I must have gone, left, and then come back to it. And if I do that, then I visited this twice, not a Hamilton circuit. This one down here, I don't have any points that are 2-valent, but if you think of wherever you start, I could finish these things, and then I could come over and I could finish these things, but when I come over and do these things, there's no way I can get from here back to here, because I have this issue of 3 pieces of it. Well, I can go down, come back, and go down. There's no way I can end where I was. So it's also a no. And I would have to go on to describe that. This is a long video. Sorry.